the exponents equal to each other. Okay, so like we did here, we said, okay, 7 to the x equals 7 to the third. The x there must be a 3, so it's got to be 7 to the third equals 7 to the third. So we're just going to see that property and we're going to kind of utilize it a little bit. Okay, so here's one like this. 3 to the x plus 1 equals 3 to the fourth. Okay. Well, that's the base to some exponent equals the base to some exponent. The 3's are equal. The bases are equal. So we know that what we can do is we can pull just the exponents and set them equal. So x plus 1 has to be equal to 4. Okay. And then that's just a nice, pretty linear equation that we can solve. We can subtract 1 from both sides of the equation. X equals 3, right? So look and see, check it, okay? If x was 3, it would be 3 plus 1, right? And that would give me 3 to the fourth. And 3 to the fourth would equal 3 to the fourth. Okay, that makes sense, okay? So sometimes it's set up very nice and pretty for me like that, and we can see, oh, those are the same bases, no problem. But occasionally it won't be set up nice and pretty like that. So what if instead of 3 to the x plus 1 equals 3 to the fourth, what if it had said 3 to the x plus 1 equals 81? Okay, now I'm looking at this thing going, okay, I don't know anything about that. And I could pull this variable out of the exponent, but only with logarithms, right? Which we can use the logarithms if we need to. But I'm going to say this is an exponential function. We're still looking at exponential properties here, so we ought to be able to do something. So hopefully you can look at 81 and say, oh, does that have anything to do with 3? Okay, and it does, right? 3 to the x plus 1 is equal to 81 is the same as 9 times 9, right? 9 times 9. And we know that 9 is the same as 3 squared, right? Okay. And then if we go one step further and use our exponent rules, this is the same as 3 to the x plus 1 equals 3 squared times 3 squared. Those have the same base. I can keep the base the same 3. And the rule for multiplying things with like exponent or like bases is add the exponents, right? So 2 plus 2 is 4. Hang on a second. That's this problem over here. Okay. So we already solved that problem. There it is. We just worked it out. So what I'm saying is occasionally, and you don't have to show all this work. If you knew that 81, oh, that's 3 times 3 times 3 times 3. Okay, then you could have just written that's 3 to the fourth and then gone and solved it. Okay, but occasionally we're going to see stuff where instead of making it nice for me and making that 3 to the something over here, they're just going to give me a number value and I'm going to have to do something with that. Okay, so let's look at another one of those and see if we can play with that number a little bit and see what it's going to be. If we can do that, then that helps me to set these things up. So what if it was 1/5 to the x, x is equal to 1 over 25. Okay. So in my head, I'm thinking, well, what can I do with the 25 to make it look like a 5 to some exponent? And I'm hoping that we're thinking, well, 25 is what? 5 squared, right? 25 is the same as 5 squared. So instead of the 25, I can just write that 5 squared, okay? Now I can look at this and say, okay, well, this is the same as 1/5 to the x. This is 1/5 squared because 1 squared is just 1, right? So that doesn't change the power. So I could rewrite this 1/5 squared if I wanted to. Okay. And now the bases there are 1/5 on both of them, right? So I've got 1/5 to the x is equal to 1/5 squared. So I can just set the exponents equal to each other. X has to be 2. And if you're not sure, you can punch this on your calculator. What if it was 1/5 to the second power? You can punch that and you'll get the same thing as the 1/25. Is that all right? Yep. Okay. So, well, maybe that one was pretty okay because it was a 5 and a 25. Let's try something else. Okay, what did we have? 4 to the x times 2 to the x squared, getting more and more complicated all the time, right? Equals 16 squared. 4 to the x times 2 to the x squared equals 16 squared. Okay. So I'm sitting here going, okay, I know that 4 is 2 squared, right? So can I rewrite the 4 as 2 squared? I'd like to do that. And the reason why I'm going for the 2 is because I see that this guy has a 2 in it. And I know that 2 is a really small number. It's a prime number. I'm going to go, if I can, down to the 2's on all of these is what I'm thinking. Okay. So 4 is 2 squared. So I'm going to rewrite 4 as 2 squared to the x power. And we'll deal with that in a second. Okay. This one times 2 to the x squared. We'll deal with you in a second. And this one, what about 16? Can I write that as a 2 to a something? 16 is 2 times 2 times 2 times 2, right? So 2 times 2 is 4, times 2 is 8, times 2 is 16. So it's 2 to the 4th. 2 to the 4th squared, okay? So make sure you can do that, just kind of playing with it a little bit. 2 times 2 times 2 times 2. Okay, 2 to the 4th. All right, so now we're going to have to use a little bit of our exponent rules to simplify this a little bit because I want all these to be 2 to the something, right? Not 2 to the something to the something. So remember the root, or I'm sorry, the rule here for when I have an exponent raised to an exponent is multiply. So exponent raised to an exponent. We multiply our exponents. We did that maybe a week or so ago whenever we were doing that exponent review, right? So we're going to multiply our exponents, okay? So this is 2 to the 2 times x is just 2x, okay? Times 2 to the x squared. Be careful with this. There's a lot of 2's running around. Okay, so 2x and x squared are different. Okay. And then this is 2 to the power or exponent to the exponent. So that's this same rule over here. We're going to multiply our exponents. So this is 2 to the 4 times 2 is 8. Okay. And if you want to check that real quickly, you can do 2 to the 8th and you can do 16 squared and you better get the same number, right? So just 16 squared is 256, right? So no matter which way I do that, I get 256. So that should check out for us. So this 2 to the 8th is equivalent to this 16 squared. They're both 256. All right. So the idea here is, did I get them all with the same base? I hope so, right? So now that I've got them all with the same base, I can do some of my exponent rule stuff. So what was that rule whenever I'm multiplying like bases? Which is what's happening over here, right? I've got a 2 to the something times a 2 to the something. Multiplying like bases, it was keep the base and add the exponents, right? Keep the base and add the exponents whenever I see things with the same base that are being multiplied. So I'm going to keep this as a 2 and I'm just going to add these exponents. Well, that's not going to add very well, right? It's 2x plus x squared. Those don't have anything in common. So I'm just going to leave them like that. And I'll probably put them in parentheses just so that we can see the whole thing. But 2x plus x squared. It's 2 raised to all of that, right? Because I add my exponents. So that's the left-hand side here. And on the right-hand side, I have 2 to the 8th. Okay. Now Now that I've got just 2 to the something equals 2 to the something, now I can use the rule we just saw a minute ago, right? Where we said, oh, if you have the same base equal to each other, then you can set the exponents equal to each other, okay? So now that I've rewritten this 5 or 6 times, now I can look at these exponents and say, oh, 2 to this thing is equal to 2 to that thing. Then the 2 exponents have to be the same. So the 2's on the bottom don't go away. I'm just only going to deal with the exponents for a second. So exponents are equal. So I'm going to pull them out. 2x plus x squared equals 8. And now I see, oh, that's a quadratic equation, right? So we've been solving quadratic equations. Hopefully you can do those. I did send, I think yesterday, I finally sent the factoring video so that you can do that. And I've got the factoring worksheet. I'll send that this afternoon. Okay, so that you can play with those if you're having trouble. All right. So let me rearrange this. It's x squared plus 2x. I'm just putting them in descending order so that my leading guy has the biggest power, right? And I want to move everything over. I've got this 8 on this side. I'm going to subtract 8 from both sides to get this guy equal to 0. So minus 8 equals 0. Now it looks like a nice, pretty quadratic that I should be able to do something with. All right. And then we're going to say, does this thing factor? And I think it will. I've got to have the a here is a 1, so don't worry about him. I've got to have factors here of 8. It's actually negative 8. That will add up to give me the 2 in the middle, right? So that's a 1 and an 8, and a 2 and a 4. And whenever I look at it, they multiply to give me a negative 8. The only way I can multiply to get a negative 8 is a positive and a negative, right? So one of these is positive, one of these is negative. And they add up to give me a positive 2, my B guy in the middle, right? Okay, so that means that the bigger number has to be positive and the smaller number has to be negative. That's how I get a positive in the middle, right? Okay. So if you're doing AC method, then you can look at this guy and go, oh, look at that. I think I can split this in the middle. This middle term, I can split him up. This one should factor by grouping at this point, once I figure out what these are going to equal. I do think that if you can do trial and error, go for it, no problem. Okay, so this is going to be minus 2x plus 4x. And whenever I look at this, I say, okay, these guys factor by grouping, factor by grouping. The first 2 guys have an x in common. That leaves me with x minus 2. The second 2 guys have a 4 in common, which should leave me with x minus 2. If I've done it right, then these things in the parentheses should match. They're twins. If you don't remember this, go watch that factoring video I sent out yesterday. The twins, I'm going to divide those out, factor them out in front, x minus 2, and I'm left with x plus 4. Okay, so that's the AC method. Remember that guy's out there. If you are struggling with factoring, then do some of that factoring review. Okay, because as you can see, this factoring stuff, it's still sticking around. We did it like week 1 and it's still sticking around. It's not going anywhere. So you got to be able to factor. Okay, if you can do this by trial and error real fast, no problem. Okay. Then I've got 2 things, x minus 2 equals 0 or x plus 4 equals 0. Solve these guys, add 2, x equals 2. And on the other side, I've got x plus 4, so I've got to subtract 4, right? Hopefully all of this has become pretty standard how to solve one of these things. Hopefully we got that by now, okay? So we've got x equals 2 and x equals negative 4. And I'm going to tell you, we've got to check some of these and make sure that they really work. Okay, so there's 2 possible answers, but that doesn't mean they're both going to work. So let's check real quickly because we ended up with a quadratic. So we ended up with 2 solutions. So go back to my very, very original. X equals 2 was one of them. Well, 4 squared is 16 plus, or I'm sorry, times, let me say out to the side here. 16 times 2 to the 2 squared. Well, 2 squared is 4. 2 to the 4th is 16. So is 16 times 16 going to give me 16 squared? Yep. That guy worked. Yay, way down here. Okay. And then I'm going to do the -4 off here to the side because I'm just out of space up there. Okay. 4 to the -4 times 2 to the -4 squared is equal to 16 squared. Okay. Well, 4 to the -4, that's going to be 1 over 4 squared, or 4 to the 4th, sorry. And -4 squared is going to be -4 times -4 is 16. So this is going to be 2 to the 16th. And they want to know if that's 16 squared. So let's just check real fast. 4 to the 4th is 256. So this is 1 over 256. This number is going to be pretty big. 2 to the 16th. 2 raised to the, oops, sorry. 2 raised to the 16th. 65,536. 16 squared, we'll find out if that's equal to 16 squared. So what we've got here is this 65,536 on top and the divide by 256 on the bottom. And sure enough, that is also true. Okay, so use your calculator if you need to. Those are kind of big numbers. All right. So they actually both work. Yay. Everybody all right? All right, I want to do one more of these because I want to get this E guy in. If you remember, we talked a little bit, I think, Wednesday about E. E has a value. We actually call him, he's like pi. E is approximately 2.72. It is not a variable. It's a constant, right? He has a value. Okay, so we're going to treat him like any other base we're going to work with. He's called the natural number. Okay, and whenever we do logarithms with him, we use the natural log, okay, ln. So the one I have here, it looks like this. If you had e to the x, oh, did somebody say something? Nope, sorry, I thought I heard something. E to the x, oh, sorry, is equal to e to the 3x plus 8, okay? Then you're just going to treat this like any other base, okay? Like any other constant that we have down there. So e to the x to equals e to the 3x plus 8. Well, those have the same base, right? So the rule we had earlier today was if two things have the same base, then, yeah, sorry about that. It's just e to the x equals e to the 3x plus 8. So if we have the same thing to same base to powers, then we can say, well, if the bases are the same, then the exponents have to be the same. So let's set those equal, and we're just going to pull them out separately, basically. Here, pull that guy out. X equals 3x plus 8. This is similar to whenever we're trying to find a domain and we just pull out the bottom of a fraction and say that guy can't equal 0. We're just going to work with just this little piece of it, okay? Well, what about that? X equals 3x plus 8. That's just a linear equation. I can solve it, right? So get all the x's on one side. I'm going to subtract 3x. Okay, that guy goes away. X minus 3x is a negative 2x equals 8. And then to get the x completely by itself, I see he's multiplied by negative 2. So I'm going to divide him by negative 2, right? And what I do to one side of my equation, I have to do to the other side of the equation. So the negative 2's go away. I've got x equals, and 8 divided by negative 2 is negative 4. Okay. All right. So hopefully we end up okay here. Questions? So we treat him just like we treat any of the other stuff. Nothing unusual. I got one more with the E that I want to look at just to make sure we're really good with our exponent rules and we can do it. So he looks like this. E to the x squared is equal to e to the 3x times 1 over e squared. Again, all of these have the same bases, so we're good to go there. So I can just pull down these exponents if I can rewrite this guy right here as e to some power. So I know it's e squared, but he's on bottom. So remember what exponent rule moves things to the bottom? What did that have to be in order for him to go to the bottom? He's not a positive. Yep, exactly. Thank you. He had to be a negative to go to the bottom. So I can rewrite this guy as e to the -2, right? E to the -2. So this is really e to the x squared equals e to the 3x times e to the -2. That's what made him go to the denominator, was the negative exponent. All right, now we are okay. Now we can work with our exponent rules. These two have the same base. They're being multiplied. So when you have same bases multiplied, you add your exponents, right? E to the x squared is equal to e to the, we're going to add these exponents because we're multiplying. So it's 3x plus -2, but a plus and a negative just is a minus. Is that okay? 3x minus 2 there. If you want to write plus negative, you can, but those will, a positive and a negative is going to become negative. And then I can use the rule we just had. When I have e to the something equals e to the something, the denominators, I'm sorry, not denominators, the bases are the same. So the exponents are equal. Okay, so I can just pull these guys down and set them equal to each other. So that's going to look like x squared equals 3x minus 2. And once again, that's a nice, pretty quadratic equation. So now we can solve this just like we've been solving all our other stuff. So I'm going to subtract 3x from both sides, and I'm going to add 2 to both sides. So this is going to look like x squared minus 3x plus 2 equals 0. And again, it comes down to a quadratic formula. Again, or a quadratic equation. If you want to use quadratic formula and do -b plus or minus all that every time you can, but I really think this is faster if we factor it. So again, those factoring skills of ours are going to be put to the test. So I need things that multiply to give me a +2, but add to give me a -3 in the middle. Again, you can do your AC method if you need to, but I think that, yep, I'm hearing it's a -1 and a -2, right? That's what I'm seeing. All right, great, thank you. So x minus 1, x minus 2. Double check yourself, make sure that works. X squared minus 2x minus x, that gives me the -3. But when I do -1 and -2, that will multiply to give me the +2. That's exactly what we wanted, right? All right, so then it's just a matter of x minus 1 equals 0 or x minus 2 equals 0. And I know you guys can solve this thing probably with your eyes closed by now. We get 2 solutions. X equals 1, x equals 2. Hopefully you're very, very comfortable with that by now. All right, so that is a wrap up of pretty much every exponential function property that I've had so far that I feel like you should be able to see by now. I want to do the logarithm graph because I want you to see why I'm telling you that logarithms are the inverse function from the exponential function. And I know we spent some time with the exponential functions, but we haven't done the log graphs yet. So I'd like to do that. Okay. All right. So if you remember, this guy, when we do as an exponential function, things look like base to the exponent equals answer. On the other side of things, the log functions, we said we can rearrange things and say log base answer equals exponent. So that our exponent on this is always by itself, right? This is our way to get the exponent down out of the exponent whenever it's a variable up there, right? I don't want to leave those up there. Okay. Log base answer equals exponent. Okay. So, and I don't know if I made this point or not, but I'm going to make it now. So what we're going to say is there's a common logarithm. Common logarithm. And what happens when we have a common logarithm is that we use the base that we're used to working in. So a common logarithm is always base 10. Okay, so remember all of our numbers that we work with in general are base 10. That's based off of the fact we think that we have 10 fingers and 10 toes. So it just works out very nice and pretty for us. So if I write something like log of x, and I don't write the base down there, okay? I don't write the base, then you can assume that that is a 10, log base 10 of x, okay? In fact, you'll do enough work with logarithms in the next week or so that you'll be like, oh, I don't even need to write that, okay? Log of x, okay? That's what we're dealing with. Whenever we have one of these things, there's a few of those little rules that start coming out, just like there were whenever we were graphing exponential functions. There is going to be some stuff that always happens when we're doing logarithm functions until we start shifting them and stuff like that, right? Okay, so they're going to say you've got some function f of x equals log base 10 of x. Okay, this is my common logarithm. These guys always graph like this before shifting. Okay, always remember, once we start transforming things and shifting and stretching and stuff, those things change stuff, right? But for our purposes, before we shift, these things are always going to be true. Okay, number one, we're going to have a point. And before the point was 0, 1, now the point is going to be 1, 0. Okay. We're always going to have a point before the function before the point was 1e or 1 base. And this one is going to be the point, the base, and then 1. And we're always going to have the point before it was the point -1 and 1 over the base, right? Now it's going to be 1 over your base, -1. So what I'm telling you is basically it's exactly the points are all flipped from what they were before. Okay. So that is, if you'll remember, that's one of the ways we know that we have an inverse function is we switch the x's and the y's, right? Okay, so here we're going to have that happening. We're going to switch the x and the y's. Okay, the last thing that's going to happen is when we were dealing with exponential functions, remember we had, here was my graph. Sorry. We had this asymptote, this horizontal asymptote at y equals 0, right? Okay. So if we flip this guy around up and invert him, that's going to turn into a vertical asymptote. Okay, so that's the fourth thing that we're going to have happening. There's a vertical asymptote at, well, if it's vertical, it's no longer y, now it's x equals 0. Okay. So these things are going to happen before I shift. Okay. So I'm picking on log base 10 because he's the natural log. He's probably fairly easy for us to do, and because I can do him in my calculator very easily. Okay. We can do this with all those other bases, like before we did 2 to the x, we can do log base 2. Okay. We did 3 to the x, we can do log base 3, but our calculators aren't going to graph those very nicely with the other bases. Okay, we have to learn some crazy buttons to push for that. Okay, so I don't want to get into that. I want to just graph the log base 10. So this is going to be good stuff for me. Okay, vertical asymptote. Let's start here. X equals 0. Okay, remember vertical asymptotes, we never ever can cross. So that means that my graph's never gonna go across this, okay? So I've got a point at 1, 0. Okay, that is right here. X equals 1, Y equals 0. I've got a point at base, comma 1. Well, my base is 10, right? So 6, 7, 8, 9, 10. I'm gonna have to kind of come out here a little bit. Okay. Right there, 10, 1. And then I've got a point at 1 over the base, which in this case, my base is 10. So 1/10. Oh man, I actually just lied to you. No, that's right. Yeah, that's right. Yeah. Sorry. I'm like trying to envision it. I'm like, it should be down here, but I was thinking I was on the wrong side. Yeah, that's right. 1/10 and -1. Okay. So these are going to be similar to the other ones that we did before. The asymptote or exponentials look like this, right? I'm just going to give you a basic. That's what y equals 10 to the x looks like, right? Okay. So they're going to be a similar shape. They're just going to shoot off to the side like this instead. So when I go to connect these dots, it looks something like that. This is y equals log base 10 of x. Okay. And so all of my logarithmic functions are going to look like that before I start shifting them. So the thing is, if you remember, whenever we were talking about inverses, and I know that was test 1, so it's been a while, but there is this symmetry around, there's a graph that goes down the middle. This line is y equals x. Okay. So if I have inverse functions, then everything that's up there that was on the exponential function should be reflected on this side of the y equals x. And sure enough, they do, right? Okay. So these guys are inverse functions. Logs are inverses. And I'm going to say inverse functions of exponential functions. They're reflected around y equals x, that axis. Okay. So sure enough, these guys are going to look just like that. Okay. They're going to have these points, and you're just going to kind of get used to seeing them and saying, oh, it's just going to kind of come, here's my x equals 0 for the vertical asymptote. It's just going to come right up against it. Remember, those asymptotes act like magnets. So it kind of sucks it up this way, and then it's going to go woo and shoot off. Okay. So let's just make sure our calculator agrees with us. When we go to graph y equals, okay, oops, I got to get rid of that stuff in there. We don't want that anymore. Okay, when we go to graph this thing, I'm going to use my log button, which is right beside my 7 key. Okay, log, and it automatically is going with natural log. So, or I'm sorry, the common log. So it's going to have a 10 down there. So I don't have to put anything in for the base. I'm just going to say log of x. Okay, because I'm trying to graph this guy, right? Log of x. And whenever I go to graph that, look right there. Okay. So it's not showing me this part down here with the vertical asymptote. It is showing me that it doesn't cross the y-axis though, right? And it just comes up, and that kind of looks like what I've got here with, we go all the way out to 10 before we go up to 1. So it's really shallow right there. Okay. It's not going to be an asymptote though, because if we went all the way out to 100, we'd be up at 2. And if we went all the way out to 1,000, we'd be up at 3. So this is growing vertically. It's just really, really slow, and it's shallow. Okay. So this is what all of these logarithmic functions are going to look like for me. So real quickly, I know I got like 3 minutes, probably 2 minutes for your bell. Okay. If I was doing this with a log base 2, like I said, that one's harder for my calculator to graph. In fact, it won't graph it just like that. I have to play with it to make it do. But we can do this very quickly, even though we don't have it on our graphing calculator, because we know what it's going to look like. There's a vertical asymptote at x equals 0. So stick that guy in there first. And then it's my points, right? I've got the point 1, 0. I've got the point, the base, which the base here is 2, 2, 1. And I've got the point 1 over the base, which is 1/2, -1. So all I have to do is put those 3 points in there, and we can connect the dots and see what it's going to look like. Okay. So 1, 0 is right there. 2, 1 is right there. And the point 1/2, -1 is down here. Okay. So here it is. Looks like that. And notice that this one's not as shallow as the 10 guy was, because he goes over to 2 and 1 very quickly. The other one had to go all the way out to 10. All right. Okay, so I'm hoping I'm beating the bell here. I hope. All right, we're done with this. I think you can start work on 4.1, 4.2, and probably 4.3. We'll wrap it on Wednesday. All right, have a great day. Thanks. Bye.